My work focuses on joint scheduling of best effort and hard deadline real-time flows in a 5G cellular system. Work under research advisors Professor Anurag Kumar and Professor Chandra Murthy. So my work is motivated by emerging industrial applications such as wireless control of mobile robots, where control packet must be delivered within strict deadline, while the same network simultaneously serves throughput-oriented FB traffic. Coming to the system model, if you think about robots moving inside factory or warehouse, like sensors on the robot send data to the controller computes control commands and are sent back to robots and the robot executes the action. So here we can see external edge-based controller connected to 5G system via wired network generates a periodic downlink control packets for the robots. Control packets enter the 5G network through the UPA before being scheduled over radio interface. The scheduling decisions are made at the GNB MAC layer, which allocates radio resources to HDR and FB users in each time slot. This figure illustrates a 5G downlink system where an edge-based controller sends a periodic control packet every 20 milliseconds to mobile robots, representing a closed-loop control with 100% activity. And each packet must be delivered within strict deadline of 20 milliseconds. And we consider the system is designed to tolerate only a very small fraction of deadline violation of 1% or like 0.5% to reflect high reliability control application. The other flow is FB, that is full buffer elastic flow, like downloading a very large file or cloud sync with an infinite backlog. The queue never empties. The scheduler at the GNB jointly allocates resources in each 0.5 millisecond slot to guarantee robot reliability while maximizing the elastic throughput. The model is grounded in real-world 5G standards as we are targeting small factories and warehouse automation. The parameters that has been set up are aligned with 3GPP QoS profile for mobile robots. This slide summarizes the modeling assumptions used in our analysis and simulation. We consider a single cell 5G downlink system with a fixed transmit power and bandwidth, and users are assumed to be stationary. We assume frequency non-selective fading, so the frequency dimension can be absorbed in the rate expression. As a result, allocating resources reduces to allocating transmission time. Control packet arrivals are periodic per slot but asynchronous across users. That is, different robots packet do not arrive at the same slot. Wireless channel includes distance dependent path loss where the fading are included relay and Nakagami, Markov fading evolutions, and fading is assumed to be independent and identically distributed across time slots and across users. Here we come to the baseline scheduling policies, semi-persistent scheduling SPS and schedule on arrival SOA. So this is the time slots divided. So every slot is of 0.5 milliseconds. Suppose a HDR of UV1 packet arrives here. If it's a SOA, that is a service on arrival, like it's a very simple scheduling policy. In a SOA, whenever the HDR packet arrives, the SOA schedules the packet immediately upon arrival using the current channel condition. So as decisions are made using only instantaneous channel condition, the scheduler does not wait or look ahead to future slots within the packet deadline window. So as the resources are assigned on demand, SOA requires a downlink control information, that is DCI, for every packet. So the UE knows where to receive the packet. So even so, UE can still slip between the UE can still slip between the successive packet arrivals. So as SOA considers only one channel realization, it often transmits in slots with a poor channel conditions. So more resources are required to deliver a packet that leads to an inefficient use of radio resources, thus degrading the FB throughput. Now we come to another baseline policy, that is SPS. Like it's a semi-persistent scheduling was designed for voice traffic packets where packet comes periodically and that needs to be delivered within a fixed delay. Suppose if the base station schedules every such packet individually, it requires a DCI, that is the downlink control information, for each packet, which creates an unnecessary overhead. To avoid this, SPS reserves a fixed amount of downlink resources periodically for the entire duration of the flow. So because the resources are fixed and known, the UE knows exactly where to look for its packet and does not require per packet downlink signaling. So this also allows the UE or the device to slip between the packet arrivals, which helps save battery power. However, the wireless channel vary over time to make sure the packets are delivered reliably even under poor channel condition. So SPS must reserve the resources conservatively. As a result, it often allocates more resources that actually needed, reducing the resources available for the other traffic. Now we come to the optimal scheduling policy, which is an opportunistic scheduling policy, which serves as a theoretical benchmark for our work. So these policies are derived from Markov decision process framework and exploit the deadline stack of the HDR packets. So the MDB formulation for asynchronous arrivals. So in every slot, the scheduler first decides which HDR. So if we come, no, first if we come to the LS opt, layered scheduling optimal policy. So here if we see in every slot, the scheduler first decides which HDR packets to serve without considering the channel condition of the FB users. The objective at this stage is to deliver the HDR packets reliably while minimizing the resource consumed. So this is the state of the MDB. So this is the RK, the rate of the traffic, delta K, where the amount of time left to be scheduled, and TK is the time required to schedule the packet. And NK decides which HDR packets are active and which are inactive, that are marked as 1 and 0 respectively. So 1 represent the active voice calls. So this is the action set, that is DK, that means which HDR packets to be served in that slot. And the reward here is the FB utility gain. So if we see a HDR packet arrived in this slot, in the third slot, so it should be scheduled within the 40 slots, that is 20 milliseconds. So the next HDR packet arrived will be on this slots. So this is the threshold evolution over deadline horizon using the Bellman recursion. So this is the Bellman recursion in the delta minus 2th slot. So if we come to the optimal policy, exhibits a threshold based structure. So LS opt, where the HDR packet scheduled without considering the FB channel states, where remaining resources are allocated to the FB flows. And J's opt is HDR and FB packet scheduled jointly, and decisions are balance HDR urgency against the elastic throughput utility. So if we see this structure, so this tau kn is the threshold sequence for every HDR flow J, where it should be 1 less than equal to k, which is less than equal to delta, and n is indicates the number of HDR UEs. TKN is the required slot fraction for the HDR user J. And UK is the FB utility index in the slot K, where UK is max of WM weight and RM is the instantaneous rate, where M indicates the number of FB users. So here we come to the heuristic scheduling policy. So the LSRDR, so it's a practical heuristic scheduling policy inspired from LSO op scheduler, while the optimal policies follows like threshold based framework, and it requires a detailed channel statistic which makes it impractical for real life scenario. So LSRDR preserves the threshold idea but removes the need of channel statistic. So in each slot, the scheduler computes the rate, that is RDR, which captures how urgent the HDR packet is. If the metric increases when the packet is close to deadline or require fewer resources to transmit. So the packet is scheduled if the metric exceeds the threshold gamma, which is dynamically tuned to meet a target packet loss probability of 1%. So this is a non-loss fare RDR. So if we see when this is a gamma, this is the RDR threshold for target aggregate HDR loss probability eta epsilon. So when the gamma is large, the scheduler becomes more conservative and it schedules only those HDR packets where channel condition is very good and are close to their deadline. This protects the FB traffic by preserving more residual resources. And when the gamma is smaller, it becomes more aggressive, more HDR packets are admitted, which reduces the packet drop but at the cost of leaving the fewer resources for the FB. So to meet a target reliability, the gamma is updated dynamically based on the observed packet loss performance. So if the observed packet loss is higher than the target, the gamma reduced to admit more HDR packets, and if loss is lower than the target, the gamma increases to improve the efficiency. So if it is a non-loss fare NLF RDR, so this is a loss fare RDR, which is a measured QN is the measured packet loss rate of HDR flow N. So this has been introduced because the QN prioritizes which HDR uses with a higher historical packet losses. Here we come to the simulation parameters, where we can see the transmit power we have set it to 250 milliwatt with carrier frequency 3.5 gigahertz, and the system bandwidth that is taken care is 40 megahertz here. If we see the number of robots, there are 100, and number of FB users, M indicated with M, is 100, and the UE there. The UEs are uniformly over disk of radius 100 meter to 500 meter, and the fairing that has been considered is relay and Nakagami 2,1, that is mean 1, and packet size of the HDR traffics are 250 bytes with control period 20 milliseconds with epsilon 0.01. So this is the rate region analysis of the two FB users at 300 meter from GNB. So if we see the midpoints, these are the proportional fare operating points that are located at the intersections of the marker where the theta 1 This is theta 1 is equal to theta 2. And this dots are the sweeping weights, that is W2, which is I have considered from 0.01 to 100 to outline the maximum capacity envelope W1 theta 1 plus W2 theta 2, where W1 I have considered to be 1. So if we compare the black line is a no HDR, the red one is a JS opt, the dashed red line is a JS RDR, the heuristic policy, and the blue one is a JS opt, where the dashed blue line is the heuristic LS RDR. And these are two are the baseline policies, where the green one is the SOA, service on arrival, and SPS is the semi persistent scheduling. So here we can see the JSOFT and JSRDR outperforms the baseline policies as well as the layered scheduling policies. This is the plot for the performance with 5 FB users, where we can see the 5 FB users are all placed at the same distance from 100 to 500 meter. And this is the performance with the 10 FB users with the same deployment of the FB users. And as we can see, from 2 FB users to 5 and 10, the JS advantages decreases over increasing the number of FB users. So coming to the detailed analysis of the LSRDR, so we have taken to the non-loss fair NLF and the loss fair layered scheduling. So there are the simulation setup consider the 100 FB users with 100 HDR users, which are uniformly distributed over a disk of 100 meter to 500 meter with fading Nakagami order 2 and mean 1. Here we can see the FB throughput, which is in Mbps, uh, where the x-axis represent the average SNR in dB. So this is the no HDR line, and this is the LSRDR upper bound with IID fading for the robots. It's a theoretically upper bound, and this is the LSRDR IID fading for the robots, and this is the LSRDR upper bound for the robot speed of 2 meter per second, and this is the so upper bounds are the theoretical and these are the simulation for 2 meter per second. So here I have considered a coherence uh, time of 2 meter per second here. So if you see, the FB throughput remains close to the Gini aided upper bound. So these are the cell edge UVs of 500 meter and these are the cell near UVs of 100 meter. So if we focus on the average SNR of 10 dB, we see the no HDR is of 2.18 Mbps and LSRDR IID is of 1.83 Mbps. And these are the two Markov LSRDR with 1.62 Mbps. So next we see the plot of overall packet loss probability versus threshold update. So this is the online tuning drives the loss probability to the target 1%. Next we have the RDR threshold versus the threshold update, where we see the larger fluctuations are under correlated fading. This is for the 2 meter per second and this is the IID fading for the robots. And next is the average SNR versus packet loss probability, where if we see there are so this is the robot speed of 2 meter per second, and this is the IID fading for the robots. So if we see the 2 meter per second, so CVL loss unfairness happens between 10 to the power minus 4 to 10 to the power minus 1 across HDR users. This is the cell edge HDR users experience a significantly higher packet loss. So the average loss target satisfied, about individual HDR users experience highly unequal reliability. So this is the loss fair RDR, which is a reliability guarantee with improved loss fairness. If we see the average SNR versus FB throughput, the throughput preserved as the non-loss fare, as we have seen in the last slide. So here in the overall packet loss probability, this average packet loss converges to 1% of loss for both the robot speed of 2 meter per second and for the IIT fading for the robots. And here, so the main plot is this one, where the packet loss probability versus the average SNR. Here, after introducing the loss fairness, so it has been reduced, so it has been improved basically. So the loss fairness has achieved from 10 to the power minus 3 to the 3 into 10 to the power minus 2 across HDR users for both the IID fading for robots as well as robot speed of 2 meter per second. Now we comes to the joint slice engineering for the FB and the HDR traffic. So here we see the packet drop probability epsilon. So here we can see the effect of the packet drop probability. This is the fading distribution where I've taken Rayleigh and Nakagami for each epsilons. This is the mean coherence time for 1, that is IID, 7 slot for, that is for the robot speed of 10 meter per second, and 36 coherence slot for robot speed of 2 meter per second. And this is for the no HDR. So this is for the no HDR geometric mean theta. It is in Mbps, and this is the LSRDR for the LF. N is the number of HDR users a system can have, and this is the geometric mean for that. And this is for the SOA. For SOA, the number of HDR users it can support in the system, and this is the geometric mean for that. So here we can see in 0.02 of epsilon, the Nakagami supports more number of HDR users than the Rayleigh has, as Rayleigh goes most of the time to the deep fade. So Nakagami supports more number of HDR users than the Rayleigh. So as we come down to 1% of packet loss, the number of HDR further reduces. And so as the epsilon, so as the packet drop probability decreases, the number of HDR as well as number of HDR UE that supports in the system also get decreases. So by seeing this table, we can understand how much our system can have the number of uh, HDR and FB users. So the future work of this is multi-cell and interference hour scheduling, extension to the interactive transfer elastic traffic, and real-time OAI testbed validation. Thank you.